Okay, so we're asked to prove the triangle inequality here using complex numbers. So what I'm going to do is I'm going to write out each statement, and I'll give a little sort of rule next to it to like describe the rule that I'm using in making the statement I'm making. So I like to start off with the fact that mod of a complex number is equal to the complex number times its conjugate. So if I had to write down the rule that I'm using, it'd be like z bar is equal to conjugate of z squared. Okay, so that's the first one there. That's the step, I guess. Remember that step to start with. We're actually squaring up the left-hand side of the thing we're asked to prove here and applying that rule that I've said. So let's move on from there. Let's work out this. Go back to purple. Let's work out that the fact that the conjugate of the sum is the same as the sum of the conjugates. So as a rule, that's like saying if you've got Z1 plus Z2's conjugates separately, that's the same as if you do Z1 plus Z2 conjugate altogether. So that's that next rule. Okay, now what are we going to do here? We're going to expand. So Z bar plus ZW conjugate plus WZ conjugate plus W bar, and all I did there was expanded. All right. Now we know that ZZ bar is just conjugate the mod of Z squared. So I'll just do that step here. And the mod of W squared. Once again, that's that rule that Z bar is equal to the mod of Z squared. Okay, let's get back to the other colour. Now, the next step is going to seem a little bit interesting, but I'll come back and explain why I've done that after the step after it. But at the moment, I'm going to write Z as the conjugate of Z, the conjugate of that. The conjugate of the conjugate of Z is Z. All right? Plus. Now I might write that the other way around. You'll see why in a tick. But I'll write Z and W and plus W's sides there. So I'll just write over here, since the conjugate of the conjugate of Z is just equal to Z. All right. Now, the product of the conjugates is equal to the conjugate of the product. So I can go that mod Z squared plus that conjugate, because we've got individual conjugates being producted and multiplied together, so we can put them together under the one conjugate sign. And that's equal to Z bar W. So that rule there is the rule that the product of the conjugates, like Z1, Z2 conjugates, is equal to the conjugate of the product. All right. Now, having got to there, we've actually got a conjugate of some complex number plus a complex number. So we've got twice the real part of that complex number. All right, so the rule that we're using there is that z plus the conjugate of z is equal to twice the real part of z. All right, now I'm going to start replacing things, but I'd just like to point out over here, I'll use a different colour in what I'm pointing out here. If I let z equal x plus iy for a tick, right? Now, x is less than or equal to the square root of x squared. Now, we know that if x is positive, well, x is equal to the square root of x squared, or 0. But if x is negative, then it's less than the square root of x squared. So that covers us. X is definitely less than or equal to the square root of x squared, right? And that is going to be less than or equal to the square root of x squared plus y squared, isn't it? All right, because that's an even bigger number, x squared plus y squared. But the square root of x squared plus y squared is the same as mod z. Okay, so x is less than or equal to mod z. Now, we know that sort of makes sense graphically too, because if you have a point, here's your complex plane. If that's your point xy, or x plus iy, then the x part is as long as the shaded bit here, but mod z is as long as that. So you can see that, I'll use a different colour to point out what I mean. Like that bit along there is the size of x, and that's mod z. Now, if x was negative, that's going to certainly make it smaller than mod z. But that might be graphically what we're talking about. But x is definitely less than or equal to mod z, right? And x is the real part, right? This is the real part of z. All right, so having said that, this step might make more sense where I decide to say, instead of twice the real part of z, I'm going to say twice the mod of this complex number. Now, you'd say, hang on a minute, then they're not equal, because twice the real part of z, which is twice x, is actually smaller. So I need to change this sign like that, because I've replaced it with something bigger. I've replaced the twice the real part of z with twice the mod of z as such. All right, so that's a little rule that I've used. Here I've said that x is less than or equal to the mod of z if z is equal to x plus iy, right? Okay, so having made that replacement, you can then say, well, we can separate out. So I'm just going to keep that sign going there and just say that's mod of z, and that's twice mod z bar mod w plus mod w squared. And that's because we're using the rule that we've used before, that z1, mod z1 times mod z2 is the same as mod of z1, z2. The modulus of the product is the same as the product of the moduluses, or the moduli if you want. It's another way to put it. So that's another rule that you've done at some point that's being applied there. So this is good revision of your complex numbers rules at the same time as doing the triangle inequality and some work on proofs and inequalities in general. Now, we know that we know that Z mod of Z bar is the same as mod of Z. So I'll write that rule down. Mod of the conjugate is the same as mod of the number itself. So we've got to there, and you can see that that means we've got mod Z plus mod W all being squared, because we've got the equivalent of a squared plus 2ab plus b squared in the line above what I just wrote. So it can be put in as an all squared. So what are we saying? If you trace back up on the left-hand side, you've got mod of Z plus W squared. So I'll just write, therefore, mod of Z plus W squared is less than or equal to mod of Z plus mod of W squared. All right, so now we can just square root that and say, well, therefore, mod of Z plus W is less than or equal to mod of Z plus mod of W. We got that by square rooting. Now, why can we do that? Well, the size of this conjugate, the size of this complex number is got to be bigger than or equal to 0. That's always the case, right? The size, the mod, is always bigger than or equal to 0. The size of Z is bigger than or equal to 0, and the size of W is bigger than or equal to 0. Therefore, we can square root like that because we've got ourselves positive numbers there that we're working with. All right, so there's a complex proof of the triangle inequality.